Good evening. Welcome to the final session of webinars series on chemistry, a collaborative seminar between the chemistry department, Faculty of Mathematics and Basic Science, Universitas Diponegoro, and Chemical Science Program, School of Distance Education, University Sains, Malaysia. Today we have two speakers that will talk about the NMR spectroscopy. The first speaker is chemist Dr. Nurul Rezali from University Sains Malaysia. And then the second speaker is Professor Bambang Cahyono from Universitas Diponegoro. But first of all, I would like to invite Professor Adi Darmawan as the head of chemistry department to give an opening speech to Professor Adi, please.
Oke, thank you very much. Terima kasih, Bu Win. Assalamualaikum warahmatullahi wabarakatuh. Today will be the last, and not the least, but actually this is the last joint webinar between Undip, within chemistry department Universitas Diponegoro and University Science Malaysia. Actually, this is very good, and we have this is the sixth science cycle, and today we have Prof Bambang, which will discuss about the unlocking of the potential of an NMR. Also, Bu Syafiqah also discuss about NMR. I would like to thank Bu Yayu that make all the things happen. Before we visit to USM, and we organize 6 webinar. Hopefully we can continue this collaboration with the others activities. I hope then I can send one of my students to do work to do research in USM. Also, what Bu Enis said before, she will go here, come to Semarang to do visiting professor. Also, Dr. Syafiqah, I think.
Tak lah. Belum.
Okay, thank you for all. Also, Prof. Dr. Tan that at the beginning contact me first. Yeah. Thank you, and hopefully we can get a lot of benefit from this webinar. That's from me. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Prof. Adi. Now let me share the CV of our first speaker. Okay, let me share my screen. Sorry. Okay, our first speaker is Nurul Rezali, PhD, senior lecturer in chemistry science program, School of Distance Education, University Sains Malaysia. She was a doctorate, a PhD. She get the PhD program in University Technology Mara, and her field of specialization is organic synthesis and natural product chemistry. As you can see on the screen, her research interest is chemical exploration and total synthesis of nitrogen and oxygen heterocycles, synthesis and structural modification of selected natural product, and isolation and characterization of bioactive natural product. Okay. As you can see, she got 3 awards. One of them is Bronze Award in the Innovation in Teaching and Learning competition in 2023. Now, chemist Dr. Nurul Syafiqah Rezali will talk about 1H and 13C NMR interpretation, organic synthesis versus natural product research. And Dr. Nurul, please present your topic about 30 minutes. And along the Dr. Nurul presentation, please for the participant, if you have any question or response, you can write your response or your question on the chat room. Okay, please, Dr. Nurul Syafiqah Rezali, the platform is yours.
Okay, terima kasih. Thank you very much, Dr. Tri Windarti. When Dr. Tri said I have about 30 minutes, I feel like I'm having my second Viva presentation. Okay, it's remind me about my PhD Viva voice last 6 years. Okay, by the way, thank you very much again. Okay, so let me share the slide first. You guys can see the screen, right? Okay.
Yes,
So,
correct.
yeah, first of all, I would like to thank to Dr. Yayu and team for not getting tired for organizing this joint webinar. As what mentioned by Prof. Adi just now, this is not the least. This is the 6th cycle of the joint webinar. And actually, I feel honored to be part of it. So inshallah, I will try to perhaps share a little knowledge that I have. Okay, so here in Malaysia, we are at 2:30, so we are all 1 hour ahead. Okay, so my sharing today is about proton and 13 carbon NMR interpretation. And I try to compare about this interpretation between organic synthesis versus natural product research. Okay, all right. Actually, I have been informed that majority of the participants for this joint webinar are among undergraduate students. So I think I would like to take this opportunity to give a glimpse to these talented young researchers on what organic chemists always do with interpretation, NMR interpretation, especially in organic synthesis and natural product research. Inshallah, hopefully, by having this sharing, some of you, we never know, right? Kita tak tahu. Some of you might feel interested to further study in organic synthesis. Okay. I would like to share a quote, a simple quote about myself. Okay, NMR has been part of my life from my undergraduate years until now. Okay, so when Dr. Yayo through Dr. Tan asking about the title for this joint webinar, I think I would like to share some about NMR. And from that, I can actually present what I have done so far. Okay, so to talk about NMR, I've been involved in this analysis, data analysis since my undergraduate studies through the final year project, which was covered on organic synthesis. And then I continue my master in natural product chemistry. So 3 years dealing with this proton and 13 carbon NMR interpretation. 2014, I went to UITM, University Technology Mara, to do my PhD. And then another 3 years and until now, okay, in USM. So allow me to share some humble efforts that have done to support talented young researchers in enhancing their NMR interpretation skills. We know in chemistry, there are several advanced instrumentations, but somehow I still think that those young researchers, when they use NMR as their main instrumentation for their research, they still need the interpretation skills, which is during my time, it's quite hard and difficult to find someone who can teach me from A to Z. Yes, we do learn about this NMR interpretation during undergraduate level, but believe me, 1 hour per week is not enough. So during the study, during my final year project, a master and PhD, I have developed these interpretation skills, and I try to help who's needed. Okay, so previously last year, I tried to propose a mapping model which can increase the student focus, and surprisingly, it won bronze. I know bronze is maybe just a little achievement for some, but for me, it's a good start. Okay, because I try to help students, and based on one article that I read before, actually there is a published article that said many young researchers, especially the undergraduate, have a difficulties to analyze the data, the raw spectrum of NMR. So from there, I try to propose a mapping model. Later, I will show you what is the mapping model. And then currently, I have organized one training course which support SDG4, which only costs about 40 ringgit. Okay, 40 ringgit, if I'm not mistaken, and I try to convert, it's about 140,000 rupiah. I think it's quite low fees for 2 days training course. Okay, full day training course. So actually for the TH and H mapping model, by the way, it's already filed for copyright. This is the mapping model. I include the multiplicity, the chemical shift, the integration number, and type of hydrogen and its neighboring hydrogen or proton in only one Excel. So student just can focus to this mapping model without feeling confused or what. So they just need to use the color code, the yellow, pink, green, orange, blue. They just need to follow the color code in order to get the type of hydrogen and neighboring hydrogen. So actually, my students or my former users think and have an options either to proceed with TH and H mapping model, or they can just proceed with the common practice. But as what I mentioned earlier, this mapping model is actually to increase the student focus. Okay, but because before this, by using the common practice, the standard approach, once the user receives the raw spectrum, they need to identify the chemical shift, the integration, and then refer to the chemical shift values table, and then go back to the raw material, the raw spectrum, to find the type of proton, refer back to the table, and then try to decide the possible neighboring proton based on the multiplicity. So this is the cycle or the common practice made by the students or by the users. But when using mapping model, they can just straightforward follow the color code, and then at the end of the day, they can just get the type of proton and neighboring proton. Okay, the second effort made was the training course, which is support SDG4, and this training course, this 2 days training course is only cost about 40 ringgit. And when we see the definition for SDG 4, everyone has the opportunity and it's actually ensure the inclusive quality education for all. So from the feedback that I received, many postgraduate students, actually I received several postgraduate students from several public universities. If you can see, it's from USM, UKM, UTM, UNISA, and even in Sabah, UMS. Okay, some of them are from UM, UTM. And I feel so happy because I'm not just helping young researchers from USM, but also from other institutions. Okay, so let's go back to the agenda of the day, okay, about organic chemistry. Okay, before that, I believe that every one of you know about this symbol, right? Okay, especially to the undergraduate students. Nowadays, this symbol is like our best friend forever. Okay, so if you ask ChatGPT what is organic chemistry and what are the two research fields in this organic chemistry, it will give this answer. Okay, so organic chemistry can be divided into two parts, the synthesis part and the natural product chemistry. And interestingly, I have done both. Okay, organic synthesis during my PhD study and natural product chemistry during my master study. If you ask me, this is actually the summary that I can provide. Okay, organic synthesis means you construct organic compound. When we are talking about organic compound, it's actually the carbon element. And of course, it also made up of hydrogen, oxygen, nitrogen, sulfur, and so on. And it can be either total synthesis or chemical explorations. And usually it's applied to develop a new medicines or drugs or for cosmetic polymers and so on. So basically in lab, you have round bottle flask, and then you have a starting material, the reagent, either electrophile or nucleophile, and then you have the specific reaction condition and solvent. At the end of the day, you have the target compounds. While for the natural product chemistry, it's from the term itself, it's actually represent the ingredients that are derived from nature and not created in lab. So based on my experience, I have experience dealing with plants. And then from there, I try to isolate and characterize those natural products. Okay, it can be either qualitative study or quantitative study. So, how does NMR play its role in organic synthesis research? It's all about compound characterization. So, this is also a summary that I prepared. It's actually to confirm a successful or failed chemical transformation, and then to confirm the functional group interconversion, to propose the structure of the compound when the targeted product fails to be obtained, and above all, the proton NMR is good enough to do all points 1 to 4. Because we know what is the starting material, we know the fundamental of organic chemistry, and from that, we can actually predict what is the obtained product based on the NMR. So I have received one example. This is actually what I have done before. So imagine we have this 5-membered ring lactam, okay, the amide, cyclic amide. So we try to number 8, okay. This is carbon number 3, 4, 5, and we assume this starting material will undergo reductive amination. But however, when we run for proton NMR, this expected proton NMR is not obtained. Okay, why we say this is the expected one? Because you see, the signal for H5 here supposedly appear as a doublet from singlet. Okay, I will not teach you about singlet or doublet, but this is how the organic chemist, specifically for organic synthesis researcher, do their work with NMR. Okay, so from doublet and from singlet to doublet, but however, unfortunately, the proton NMR that you get is still singlet. So from there, you need to compare it with starting material and see what is the difference. So this is the proton NMR for starting material, while here is the proton NMR that you have obtained after the reaction. So only one difference, which the broad signal, okay, from 10 something, the chemical shift 10 something, move upfield around 4 something, and the integration is different from proton 1 proton to 2 proton. So from there, you need to use your fundamental, your basic organic chemistry to propose the structure. Okay, so you must know what is the reaction mechanism. Reaction mechanism is the curve arrow that your lecturer always asks. Okay, draw the reaction mechanism from nucleophile to electrophile, okay, from electron-rich species and so on. So if you try to summarize that this reductive amination is failed, then you need to propose one product, okay, one obtained product based on the NMR. Okay, this is the second example when you use the quite similar starting material, and you aim for carbon alkylation, where you use the methyl iodide, for example, as electrophile to insert the methyl group at carbon number 4. So based on the proton NMR, you are not obtaining this expected proton NMR. So you see, the proton here at my cursor supposedly change from doublet to singlet, but however, you can still see the signal of doublet remains doublet. Okay, so meaning that the C alkylation does not occur. So go back to your organic chemistry notes and see what is the possible reaction can take place when you have the electrophile. So in that case, no C alkylation occurred, so it proceeds with O alkylation, where the electrophile, okay, the methyl from methyl iodide is actually bonded to the oxygen atom. So I also have another 2 examples. Okay, this is a compound that has been synthesized by one of postgraduate students from UMS. So it has this one, okay, the shift-based proton and 3 aromatic protons. So the challenges occur when you need to identify any equivalent protons. For example, in this structure, you have 3 sets of aromatic compound, okay, the aromatic rings. So how to differentiate between H2 and H13, H3 and H12, and so on. So the multiplicity of each proton also been considered. So from there, you need to identify it, and you need to use again your fundamental on organic chemistry. So you should know that the hydrogen at position number 2 is deshielded compared to the proton at position 13 due to the location near to the cyclotriphosphazion, which involve the electron delocalization. And H12 is shielded or upfield compared to H13 due to the position again to the nearest electronegative effect of the chlorine atom. So from there, you can differentiate which signal is which. Okay, so we try to first use the NMR and use the knowledge that you learn in class to assign for each proton. Then we try to verify it using COSY, the 2D NMR, and see some correlation. So for example, H2 and H12 and H13 are close or next to each other. So supposedly you will see the correlation between them. And this square shape of correlation show that H12 and H13 are next to each other. If you cannot see the square pattern, means the hydrogen is far to each other. Okay, And then you can also use the HSQC or HMQC to show the attachment of proton and its respective carbon. And you can also use other analysis such as 13 carbon and depth. But again and again, if you go for organic synthesis, proton NMR is good enough. Okay, you can use other data for verification. Okay, and the second example use the same structure when you have the derivative, the analogs. So how to differentiate between one analog to another analog? So if you compare both compounds, one contain chlorine atom and another compound contain alkyl group, the pentyl. Okay, so you must expect to see that pentyl or that aliphatic chain in the NMR. So if you have only chlorine attached to that benzene ring, you will not see any signals upfield. Okay, but if you have C5 H11 just now, you will expect it to see some of the methyl and methylene signals, which give integration 3 and 2 integration each. So this is actually what organic chemists did with their proton NMR. Okay, and allow me to share some previous works. Previously, we have synthesized the triazoles and quinolone derivatives, and both compound has been assessed against anti-malaria, okay, using Plasmodium knowlesi A1H1. So this work integrated researcher from UKM and UM from Malaysia, and you will see for each functional group interconversion involve NMR. So you need to run and analyze the NMR data one to one another. While here is the amido substituted 1,3-diarrhea-propane using head cross coupling reaction. When we have the alkene functionalities, we try to couple, okay, with the amide functionalities that contain this living group. So at the end of the day, we will have this 1,3-diarrhea-propane, and this structure has a cytotoxic effects against breast cancer cells. And this is the exploration, okay, of the functional groups available in quinolactosine derivatives. So we did several synthetic routes that includes intramolecular cyclization, acylation, Diels-Alder, and hydrogenation. A simple chemical reactions, the common chemical reactions in a lab, but we can figure out the possible functional group interconversion even in a small compound. Okay, all right. Now we move to the second part of the sharing, which is NMR in natural product research. How does NMR play its role? Right now, I hope every one of you can get the main idea of NMR in organic synthesis, where proton NMR plays a crucial role, okay, in order to confirm either the reaction success or fail. If fail, then you need to propose a possible structure for that compound based on the knowledge, based on the fundamental of organic chemistry that you learned. And from there, you need to use 13 carbon depth and 2D NMR to validate or to verify your proposed structure. Okay, now we move to the second part, natural product research. Okay, as mentioned earlier, natural product research is where you try to isolate a chemical compound from a plant, and you will have no idea what is the structure of that natural product. Okay, so meaning that you try to determine the structure of an unknown, and in that case, proton NMR is not enough. Okay, it's highly need other NMR data such as carbon, depth, and also 2D NMR. 2D is including COSY, HMQC, and HMBC. So some challenges about natural product research, sometimes your proton NMR will not so clean, okay? But you can see the integration from there. So it's more like you play puzzle when you receive the raw data of proton NMR, okay? So if you see the integration for each signal, you can validate that these signals is possible for aromatic protons. While here, since it is 2H each, so most probably those signals belongs to the methylene protons. Okay, so for example, you have this proton NMR. Okay, so you assume that it's actually the aromatic protons. So try to use additional information. You can run for IR, you can see the TLC profile, or you can run for MS. But if you go straight away to the mass spec MS, you will be again so clueless because MS has its own library. So for example, AMPERZ 150. So it will suggest various structures that has molecular weight 150. So we want to make our analysis become or having some hint. So try to go for IR first. Okay, so if you assume that in the structure, if the unknown has the aromatic protons, then you can go for IR. So everyone know, okay, that the stretching bands for CC aromatic is 1,400 something and 1,600 something. But okay, once you receive that, you also can see or observe there are two stretching bands, strong stretching bands that assigned for carbonyl and for the hydroxyl. So you might expect to have the carbonyl compounds. So when you see there is OH in the compound, you can have either carboxylic acid or normal alcohol. Okay, but whatever it is, now you have an idea that the structure of unknown contain phenyl group and also the carbonyl functionalities. All right, so we try to assume that the unknown is contain carbonyl functionalities, either as carboxylic acid or free OH. Okay, so you go for 13 carbon NMR, okay, and try to figure out either it's really carboxylic acid or aldehydes or ketone. So based on the analysis, you can see this clear 13 carbon NMR, okay, and these signals is actually belongs to the carbonyl of aldehydes or ketone. So you can eliminate or discard your assumption that the unknown is actually the carboxylic acid. So you can go for aldehydes and ketones. But however, if you refer back to the proton NMR, you don't see any hydrogen for aldehyde, which is always appear around 9 ppm. So between aldehyde or ketone, of course, our unknown might go for ketone. So we try to go for another analysis or get some more information, either this unknown is correct as a ketone or not. So try to use that, okay? From this that you can actually differentiate the existence of methyl group, methylene group, or methine group. So based on this depth 135, you can see that many signals here at upfield region appear as a CH2 carbon. Okay, so many CH2 carbon in the structure, and you have the CH aromatic, while any absence signals at depth is actually belongs to the quaternary carbon, include the carbonyl. So you can go for HMQC and see the correct attachment for each hydrogen signal and its carbon signal, but still you cannot get an idea. You can just have an idea. This methylene carbon is actually belongs to all signals that appear upfield in proton NMR. Okay, and then the fourth key point that you can observe when you do natural product chemistry, try to compare values, the NMR values, with literature for compound that has been previously isolated. So typically the same genus or family contains the same compounds. So since this structure is, this unknown is isolated from Zingibraceae family plant, so I try to figure out what compounds that usually has the phenol, has the aromatic ring and many CH2. Furthermore, when I ran for its DLC, it give a good blue spot. Okay, so based on the literature, the most possible compound skeleton is the diaryl heptanoate. So I tried to figure out some of these diaryl heptanoate from Zingibraceae, and from there, I know this unknown is actually this compound. So I tried to run for HMPC to verify the proposed structure, and based on the analysis, I can conclude that this unknown is actually belongs to this diaryl heptanoate. So it's not a carboxylic acid, it's a ketone, and you have a series of methylene carbons here, and the OH that you observe in IR is actually belongs to the free hydroxyl group in the compound. Okay, and in order to further validate the proposed structure, I try to use mass spec, and when I run, it's give molecular ion peak 314, and from there we try to figure out what is the base peak, okay, and other fragment ions. So this is the base peak 107. So it's actually due to the beta cleavage of C1 and C2 to give the benzylic carbocation to form the tropylium ion. So this is something that natural product chemists always do when they did the isolation and structural elucidation. They will use all the fundamental basic organic chemistry knowledge that they learn during in a class to this single structural elucidation. So for other significant fragment ions, we also need to give its suitable fragment ion of fragmentations. So from there, we try to propose this. Okay, you know about the alpha cleavage, beta cleavage. So from there, it gives the tropylium ion, which is very stable. So that's why it gives a base peak. So after all this verification, will double confirm that your proposed structure for the unknown is correct. Okay, so at the end of the day, you need to summarize everything to show and give a correct labeling to the unknown by using 1D and 2D NMR. Okay, and of course, the IR, the UV, the TLC profile, the mass spec will support the suggestion, the assumption. Okay, so allow me to share another structural elucidation made from species Amomum oleaginosum from family Zingibraceae, which contain the flavone, the flavanone, the diterpenes. Okay, so the difference between compound 4 and 5 is actually the reduction of aldehyde from this to this, okay, methylene hydroxyl and the stigmasterol. While from this actino Daphne Prunos from family Laraceae, we managed to isolate and characterize the alkaloids, okay, the alkaloids such as boltin, norboltin, laurotetanine, and so forth. Okay, so I think that's all from me. Thank you very much. You can reach me at this email address. And if you are interested to come to USM and do some works on organic synthesis and natural products, you can reach me, inshallah. Thank you.
Thank you, Dr. Nurul Syafiqah. It's very interesting. But we have to keep our question after Professor Dr. Bambang presents his topic. And before Professor Bambang share the topic, I will share the CV. Okay, it's quite long. Okay, Professor Bambang Cahyono is a lecturer in organic chemistry, in Department of Chemistry, Faculty of Science and Mathematics, Diponegoro University. He has a lot of publication. You can go to the Google Scholar or ResearchGates or the Scopus.com. And Professor Bambang has a lot of patent and commercial product. One of them is the formula for lowering blood sugar and improving erectile function. The synergy of kefir, powoceng, pimpinella, alpinbong, and cabai Jawa. And he also has a mark that is Mega Power Herb Drink and La Frontier. I don't know where can we get this product. Maybe we can ask Prof Bambang later. And for the structural position, he is the Deputy of Quality Assurance of Integrated Laboratory in Universitas Diponegoro from 2016. And for the publication, the latest publication is about quantitative analysis of a drograpolite in Sambiloto, herbal preparation using UV-Vis, HPLC, and 1H-NMR with the benzyl ether as internal standard. Okay, Professor Dr. Bambang Cahyono, the time is yours. Please, 30 minutes, yeah. Okay, Prof. Bambang, the floor is yours.
Okay,
We'll
thank
stop
you very much.
sharing.
Sorry, ayo. Ini kenapa nih? Ntar bisa diangkat. Iya. Iya. Oke, share.
Yeah. Then choose the screen.
Okay. Tunggu. Please. Share. Tadi kuat toh. Oke.
Then choose the screen of your
Sekarang
presentation.
Oke.
The wrong screen, I think, Pak Bambang. You have to choose the screen of your, this one.
I'm sorry, I have to adjust Professor Nurul topic, and I must to remember what I have done 25 years ago, Doctor.
Masya Allah.
So presenter showing, oke. Kelihatan ya itu. Oke. Pointer, oke. And laser point, oke. Good afternoon, everyone. Good evening, ya.
Full screen,
Masih
Pak
ada.
Bambang.
Okay. Yeah. What I must do for this one.
Full screen.
Mhm.
Nah, this one, and then click next.
Mhm.
Full screen kan.
Next.
Yes, I-
Next.
Oke. Full screen.
Yes. Next. Use next.
So presenter view tuh.
Okay.
Oke. Itu kelihatan ya.
Once.
Kelihatan ya. Top step. What I must do ya. Jadi aku harus
Let
I
me.
must ya.
Or maybe you
Because-
can just share your flight or your file to me, Prof Bambang, so I can share to you.
Oh, oke.
Using
Yeah.
WA is okay.
Mm-mm. Mungkin di dulu apa pertanyaan dulu saya. Oke. Ya.
Filenya kirim ke saya saja, Pak Bambang.
This one, oke.
Okay.
Mm-mm.
Nah, just using
Ah, okay, that's good. So we can
No.
see.
Not
Yeah.
yet. Klik kanan.
Oh, no.
Klik
Oh,
kanan.
ini aja deh. Ini aja deh. Klik aja. Nggak mau ya.
Ini. Mungkin dulu. Coba dianukan dulu.
Kirim ke saya, Pak Bambang.
Oke.
Kirim ke WA saya.
Masih kelihatan juga.
Ke WA saja.
Masih kelihatan ya. Terus ya. Coba. Oke ya. Oke, good afternoon everyone. I'm sorry. My English may not so good like Dr. Nurul because my second language is French. So I will be using a mixed English and sometime in Malaysia. I hope that's okay. Well, in 30 minutes I'd like to share a few ideas. I believe it's the role of the lecture in Indonesia to broaden student perspective and ensure the research funding and apply it in daily life. For that reason, I'll spend about 10 minutes on the main topic and use the rest of the time to share insight. Yesterday, Prof. Nurul discussed the basic of the using NMR for identifying molecular structure. In Indonesia, there's a talk in the illustration of the organic molecular structure course. Today, I'll focus on proton NMR from a quantitative perspective, which is not yet widely included in Indonesia curricula. Perhaps we could suggest adding that at Undip in the future. These are two main points we'll cover this afternoon. Okay. Before we delve into the main topic, I'd like to share a nostalgic story from my youth. When I was 17, about 44 years ago, I visited Borobudur Temple, one of the 7 wonders of the world. There, I touched a stupa believed to grant wish, and wish become to a chemist and study a great university in Indonesia and abroad. Alhamdulillah, that wish come true. I complete my undergraduate and postgraduate studies at IITB Bandung, and earned my doctorate at École Nationale de Chimie Montpellier, France. I also wish to become a teacher, and now I am lecturer in organic chemistry at Undip. Even my wish for a beautiful wife was granted. Ya. Saya mendapatkan istri yang cantik juga. I married with Professor Manny Suseri. Ya. Dia ada di sini. If you ever visit Borobudur, try making a wish true. You know, it may come true. Mungkin ya. Borobudur also tell the story of how Indonesians have been using herbal plant for traditional medicine since 8th century. This traditional has continued for over 1,300 years. And last year, UNESCO recognized jamu as Indonesia intangible cultural heritage. Borobudur is close to Undip, just 1 hour's drive or maybe even faster when the new toll road is complete. So if you visit Borobudur, please stop by Undip too. You make meet your soulmate here for student. During my undergraduate years, I worked on toxoflavin analysis 1987. Well, udah lama nih. Back then, I had to manually calculate the area under an XPLC chromatogram. If the peak wasn't symmetrical, I had to cut it out. I had to cut with it and calculate its area. Now, with a modern digital technology, we simply press a button and the integral of the peak representation or representing concentration appears. This principle applies to all quantitative analysis techniques, including chromatography and spectroscopy. I am grateful that back in 92, my institute, where I studied, already had NMR, UV, infrared spectroscopy, and HPLC. My message for students, always master the fundamental of science, even in this digital era where everything seems easy with just a button press. Ayo. Yeah, my master research focused on hypochlorination of cinnamic acid, and my doctoral research was on organic synthesis, which I will discuss today. While pursuing my doctoral in France, I was also active in cultural and student organization under the guidance of Professor Christo and Mademoiselle Francois Plena. Okay. Why did my focus shift to the analysis of organic compound? This question. The answer lies in the demand of my institution. Since 2023, I've been part of the core team established the Natural Medicine Institute and managing the Natural Medicine Development Center. The center is collaboration between Undip and the Central Java Regional Government. I'm sorry. Currently, I also deputy quality assurance at the integrated laboratory, where Undip's advanced equipment is centralized in one building. XPS and TEM are expensive. We have now. They could buy you 20 Toyota Alphard cars, barangkali harganya sama dengan 30 harga Toyota Alphard ini ya, dua alat ini ya. Hence many my publication focus on the standardization of herbal medicine, an important task assigned to me by my institution. Okay. Prof. Manny summarized the roadmap for developing natural medicine at Undip, which has been applied in the chemistry department was established in 1989. This roadmap remains relevant today. All natural medicine development starts with identifying the type and the quantity of active compound in plant, as the efficacy and toxicity of herbal medicine depend on these two factors. This is a simple roadmap of the research conducted from 2018 to 2027. The main focus of the research is divided into two areas. Product development community need section in this section A. This area centered on developing formula through scientific testing aimed to creating useful product for society. The outcome included patent, prototype, and collaborative partnership. Development of and evaluation of testing method for active compound, section B. This focus on refining and assessing method to determine the presence and quantity of active compound. Ultimately, this led to the creation of academic document that the government can use to improve for further development traditional medicine. These are the two main topics will be discussed today. The primary focus today is on the use of NMR for quantitative analysis, which fall under the standardization of natural medicine, or section B. Let's begin with focus area A, which center on research aimed to developing product formula that are in demand by the community. As a chemist, the starting point of the research is understanding the mechanism of action active component within plant extract. Therefore, studying the relationship between structure and activity QSAR is crucial. The patent for a blood sugar lowering and erectile function improving formula comprising kefir, perwoceng, and cabai Jawa was granted in 1980. Yeah. Scientifically, this is due to piperin in Java chili, Piper retrovatum, which can increase the GMP enzyme in the pineal canal. My hypothesis was that extract of this plant could enhance erectile function due to the presence of piperin, an alkaloid with a structure similar to sildenafil, or commonly known as Viagra. Although this herbal formula for enhancing erectile function is highly appealing, bringing its commercialization have proven challenging. Upon investigating the reason behind this difficulty, I identified the following key issues. In the first, ethical clearance exists. However, the proposal details are incomplete and fall short of BPOM is Indonesian FDA inspection. There is no standardization of medicinal ingredient. This is two issues. Set extract, nor is there is any standardization of the final product or formula. In the third, the production process remains on a small scale and does not meet good manufacture practice or GMP for traditional medicine, which requires collaboration with large traditional medicine. Building on this experience, I am now working to address the shortcoming in the product I developed. This is one of the products currently undergoing formulation and standardization, focusing both on the raw extract material and the final formula. Why did we choose this product? In the first, issues like concentration, fatigue, and decreased motivation often hinders productivity among students and young professionals. And the second, herbal supplements are increasingly popular among younger generation. So we opted for an effervescent form to align with their task preference. After critical review, we initially developed 3 formula. However, we agreed to eliminate the third formula due to a challenge to sourcing its raw material. Nah, ini dengarkan musik sebentar. No problem. Okay. The next presentation will focus more on research related to the standardization of active ingredient. I'm working on creating a formula to transform between a standard and active ingredient analysis. Simply put, like this. Bambang is 3 times more handsome than a Korean movie star, Lee Min-ho. And Mr. Parsarwan, hello, Mr. Parsarwan, on the other hand, is twice as handsome as Choi Siwon. Now, can I say that Bambang is more handsome than Parsarwan? Of course not, even if it may actually be true. Just kidding, Mas Parsarwan. Yeah. So, why I'm developing this formula? In the Indonesian herbal pharmacopoeia, the standard for total flavonoid content varies for each plant, as the procedure are tailored to the specific active compound of each plant. For example, I know 3 standards for 5 different plants. Standards like quercetin or rutin are commonly used and quite affordable, but using apigenin is very expensive. Moreover, if we look at the activity effect, both flavonoid and phenolic exhibit the same effects, function, antioxidant activity. So, according to the literature, there are already many studies on total phenolic and total flavonoid, but they often use different standards. This variability in standard complicated our task as data user in predicting which plant material has better quality. For example, here we see that 4 researchers use a quercetin as a standard. While another 4 researchers use a routine as a standard. Okay. So how can we compare which one is superior, green tea or propolis? After conducting a series of analytic research steps, we have proposed a formula for converting total flavonoid content based on quercetin standard to routine or vice versa. We have conducted analysis on several natural medicine ingredient lists in the Indonesian herbal pharmacopoeia, and statistical tests show that the results were consistent with laboratory findings. With this equation, I have successfully unfired data from around the world. This formula has been beneficial for all of you. Currently, I am still working on conversion formula for other compound. For instance, I have for apigenin or another flavonoid. The same approach can be applied to total phenolic analysis. By developing conversion formula, we can facilitate comparison across study, regardless of the standard issue. This is showing the difference between the calculation using my proposed formula and the laboratory analysis result. Statistically, the value are the same. Now, if you have data based on catechin equivalent, for example, you can convert it to gallic acid equivalent. Now, Mr. Bambang can compare to Master Parsarwan. This is an undergraduate student publication in a well-accredited journal in Indonesian. Many people have commented that it should have been submitted to a Scopus Index journal. All my undergraduate students are also enthusiastic about publishing. This is also draft publication by undergraduate student. We plan to add more data to include a total of 20 extract and 5 flavonoid standard, with the goal of qualifying for a Scopus journal. Ini lewat aja. There is actually a more problem I like to discuss, but it make better to save it for next meeting. As part of standardization effort, we have developed a systematic isolation method for high-cost active compound standard. For example, piperin from black paper or paper retrofactum will be offered at an affordable price, whereas pure isolated dimethoxycurcumin, bis-dimethoxycurcumin, and curcumin will be priced higher due to their limited available in the market. Similarly, heptolite is rare compound, so I will also price accordingly. Achieving a certificate reference CRM status for this compound is challenged, as it requires multiple rigorous steps. In light with this award, we are committed to providing high-quality standard compound with the goal of establishing them a certificate reference material to support reliable standardization practice. Nah, ini. Currently, Prof. many group is working on transformation heptolite compound to produce derivative with better bioavailability. This material also represents new organic compound anticipated to serve as novel activity ingredient. This transformation involves addition reaction to alkene double bond, one for addition reaction in alpha beta unsaturated lactone system and diasalder, and the third ester hydrolysis to yield alcohol derivative. As future chemists, students should not only develop and disseminate scientific knowledge both nationally and internationally, but also contribute to the government, policymaker, industry, and society. Your basic knowledge of chemistry is essential for this contribution. Here is a photo of me with the head of the Indonesian Food and Drug Authority atau Badan POM, representing of the Indonesian Natural Medicine Industry Association, and director of 2 natural medicine factories in Indonesia. They are very helpful every time we conduct research. Well, all right, let's now move to the second topic of our discussion, the application of proton and amber for the quantification of organic compound. I'd like to share my experience pushing the doctoral at the École Nationale de Chimie Montpellier, France, from 94 to 97. Don't worry, my thesis was very thin, only 70 pages, yeah? Even less than the average undergraduate thesis. Are you ready? What did I work in during my PhD? Nucleophilic substitution reaction. I'm sure you are all familiar with this concept. Generally, we use the alkyl halide model where CCl is substituted by C nucleophile. The same principle applies to quaternary ammonium compound, C and plus methyl, where the electron glued is drawing toward the electron deficient nitrogen, causing the bond to break and allowing substitution by a nucleophile. For example, if I react the 3-methylamine with ethyl chloride, it produce ethyl 3-methyl. I'm sorry. Sampai di mana ini tadi? Oke. Ini gimana? I'm sorry. Beda ya?
Sama Pak. Sama Pak.
Yeah, okay. For example, if I react 3-methylamine with ethyl chloride, it produces ethyl 3-methyl ammonium chloride. That is true. When this is further react with a bulky nucleophile, like a 3-phenylphosphate or lithium diphenyl phosphide, the methyl group is attacked, resulting in ethyl dimethylamine. If I use a propyl chloride, the product is propyl 3-methyl ammonium chloride, which can then become propyl dimethylamine, and so on and so on. Now, if I react 10 alkyl halide with 3-methylamine, how many new compound will produce? 10? No, I will produce 20 new compound. If I test their biology activity, I will have a 20 data point for QSAR, Quantitative Structure Activity Relationship Analysis. Testing this on 10 microorganisms would generate 200 data points. Imagine the insect could uncover. This is approach. Approach isn't limited to synthetic compound. When applied to natural product, like your compound, Dr. Nurul, like the analgesic alkaloid thebain, reacting it with a propyl or isopropyl or ethyl group could reveal the relation between structure and biology activity. This is what makes organic chemistry fascinating. I perform a dequaternization reaction on 3-methylphenylammonium under an inert nitrogen atmosphere. I stir and heat the reaction and discover that the anion act as a nucleophile, dapat berfungsi sebagai nucleophile. The reaction was analyzing by using NMR. In this table, we see the foundation parameter for using NMR to calculate the progress of the demethylation reaction from 3-methylammonium to dimethylamine with the benzyl ether as the internal standard. Firstly, 3-methylphenylammonium has a chemical shape at 3.7 ppm with 9 protons, which will monitor as it decreases in intensity as the reaction proceeds. Secondly, the product dimethylphenylamine appears at 3.0 ppm with 6 protons, and we will observe in the increase in its intensity as it forms. Lastly, the benzyl ether at 4.6 ppm with 4 protons serve as a stable internal standard. By comparing the integral reaction ratio of this signal relative to the fixed integral of the benzyl ether, we can accurately calculate the reaction progress. In summary, this table provides a straightforward by the use proton ratio and integral chain to track the demethylation reaction completion with the benzyl ether as consistent reference. Bu, I'm sorry, Bu ini lanjut. This slide show
Prof.
that
Bambang.
yeah.
5 minutes maybe, yeah.
Yeah. This slide shows the NMR spectrum of trimethylphenyl ammonium chloride, which are our starting material in this reaction. In the spectrum, we can observe distinct peak corresponding to the different proton environment with the molecule. At 3.7 ppm, there is a strong signal representing the 9 proton from the 3-methyl group attached to the nitrogen. This peak is significant as allow us to track the methyl group especially in our reaction monitoring. Between 7 and 7.3 ppm, we see a peak corresponding to the aromatic proton on the phenyl ring. This region reflects the characteristic chemical shape for aromatic proton, helping confirm the identity and structure of the starting compound. By analyzing this peak, we have a clear baseline for the reaction starting point. As the reaction progresses, we will monitor change in this specific signal, particularly the methyl proton, to quantitate the demethylation process and assess the reaction completion. This is the proton MBR spectrum of dimethylphenylamine. There are 2 types of proton, 6-methyl proton in the chemical safe region around 3 ppm and aromatic proton in the 7 to 8 ppm ring with 5 protons. Actually, we can directly calculate the yield of percentage of transformation by comparing the integral of the amine product proton. There are 6 proton with the remaining ammonium proton, which has 9 proton. This is NMR spectrum indicated that the reaction has reached 50 completion. Here's how we determine this by examining the integration ratio of the main signal. Ammonium appears around 3.7 ppm with a higher integration. Amine appeared around 3 ppm. The 3:2 integration ratio between ammonium and amine suggested that half of the ammonium has been converted to amine, while the other half remain unchanged. In other words, the ratio confirms that the reaction is 50% complete. This slide shows the NMR spectra analysis to demethylation react at 75 completion. Yeah. In the spectrum, the absorbed band of signal in the ammonium region indicate that the reaction is complete. However, I was not satisfied with this direct approach because there is a possibility that the amine compound may escape during the reaction or evaporate when I replace the solvent with deuteric chloroform. To overcome this, I use an internal standard, specifically the benzyl ether. Why the benzyl ether? In the first, it gave 2 distinct signals on the NMR spectrum. And the second, it has a high boiling point, 300 degrees, and is chemically inert, making it stable during the reaction. Here's an NMR spectrum of the benzyl ether. 4 benzylic proton at 4.5 ppm and 10 aromatic proton in 7 to 8 ppm ring. For a clear illustration, suppose I start with 1 mole of 3-methylphenylammonium, perform the reaction, and add 1 mole of dibenzyl ether as the internal standard after the reaction. Then I replace the solvent with CdCl3 and obtain this NMR. The peak ratio in the 4.9 ppm region, dibenzyl ether for proton, to the 3 ppm region, 3-methylammonium with 9 proton, is 4 to 9. This indicates that the demethylation reaction has not occurred because the mole ratio of 3-methylammonium and dibenzyl ether remains the same. In the start, where the reaction has reached only 20%, we can observe the relationship between the integral ratio and mole equivalent to quantity reaction progress. Ammonium, as the starting compound, has an integral ratio of 6.7 and mole equivalent of 0.7. Indicating that 70% of this compound remain. The amine product has an integral ratio of 2.25 and mole equivalent of 0.25, meaning that 25% of the ammonium has been converted into amine. Dibenzyl ether serving as a constant internal standard with an integrate of 4 and mole equivalent of 1 provide a reference to ensure accurate quantitative measurement. By observing change in the integral ratio and mole equivalent of each compound, we can clearly see that the reaction has progressed to 25%. What if the NMR spectrum like this? Here, the reaction has progressed 75%. This NMR spectrum confirms the complete reaction progress, yielding dimethylphenylamine as the final product. The 3-methylphenylammonium signal has disappeared, indicating that 100 conversion. Additionally, the integration ratio between dibenzyl ether and dimethylphenylamine match the expected mole ratio. This consistent further verified the accuracy of the reaction yield and confirmed the analysis integrity. Using this approach, I was able to successfully determine the reaction kinetic of the demethylation of quaternary ammonium compound as shown in this graph. This illustrated how NMR can be effectively used to quantity reaction kinetic. This is just a small part of the data set while 3 points from the graph, but it can provide valuable insight into how to quantify an organic compound using proton NMR. Remember, each time we perform one quantity measurement, data reliability is essential. And here is the precision data for the measurement. Now, it should be clear how proton NMR can be used to quantify reaction kinetic. These are the quantification results from several reactions in my PhD dissertation. Standardizing active compound or organic compound with NMR offers several key advantages. First, NMR enables direct quantitative analysis without the need for multiple external standards, which are often expensive and vary widely in price. With one stable internal standard, we can replace numerous costly external standards. One standard for all. Second, the NMR is non-destructor method. So the sample remain tag and can be reused after measurement, and so on and so on. This is an example of how NMR can assist in analyzing to bioactive compound under graphite in market available medicine. Hasnabila, hello Hasnabila, a master student in chemistry at Undip has conducted this research and has been published in international journal. Please feel free to contact her for further discussion. Finally, here's the pricing for conducting quantitative analysis with NMR and at Undip. We are proud to say that Undip Integrated Laboratory is the only one in Indonesia capable of performing quantitative analysis with NMR. Give it a round of applause. Looking at the price list, you make realize how valuable the technique is. You should also be curious about how TMS can serve an internal standard. Hello. Here's one limitation. Please think about what is MACD. Apa yang menjadi kendala utama apabila kita menggunakan TMS as standard internal. Yeah. I will leave that as homework for you to explore. In closing, I hope this presentation has shown how much chemists contribute to society, industry, and policymaker alongside the professional. I also hope this session motivate you to explore and applying your chemistry knowledge for the greater good. Stay healthy and successful always. Feel free to discuss this with me via WhatsApp or email. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh. Thank you very much.
Thank you, Professor Bambang. Very interesting. And now, the question and answer session. For the speaker, please see the chat room. I think we have 3 questions from Bu Yayu. Okay. I will read the question. For both speaker, is it enough if we want to determine the structure of organic compound, especially only using 8 NMR? Okay, and then the second question.
NMR, yeah. Or using only NMR.
Only NMR or?
Yeah, it can be NMR or CNMR. So like that.
Just one, yeah. And then the second question, what is the most sophisticated instrument if I want to elucidate the structure of organic compound? Okay, maybe Dr. Nurul Syafiqah first.
Okay, thank you, Dr. Tri. Dr. Yayu, I feel so nervous to answer the question. Okay, if we do the synthesis, doesn't matter organic or inorganic, as long as it has proton and carbon, so it can go for proton and carbon NMR analysis. And at the same time, you already know what is your starting material, what is your expected product. So you can just confirm it using NMR. Okay, but if you would like to know about the bond length, the bond angle, of course you must go for example. For example, that compound is in crystal form, so you can go for crystallography. But to confirm the position, the functional group interconversion, as long as it has proton and carbon, then you can go for NMR. I have experience where I need to evaluate the master thesis made by organometallic students, organometallic field student, where it has a metal center atom, but that metal center atom is bonded to the organic ligand. So I still need to evaluate, does the NMR analysis fit that organic ligand or not? Okay, and then the second question, the most sophisticated instrument, if you go for natural product chemistry, you still know the unknown. So the best thing that you can go first is NMR. But for synthesis, you have other choice other than NMR.
Okay, thank you. I will
Thank you,
continue
Dr.
the
Syafiqah.
question from Bu Yayu. How if I have to choose between 1H NMR and 13C NMR, which one is the best?
Okay, both has their own functionality. I mean, proton NMR will give you more informations because specifically it will tell you who is the neighboring protons. For example, you have CH2. You will know who is the next to that CH2. Okay, we know that carbon mass has 4 bonds. So we from proton NMR we will know who are the 2 atoms that bonded to that CH2. Compared to carbon, you might have no idea because from its NMR, the signal only appear as a singlet. It doesn't have multiplicity, doublet ke triplet or quartet. So you may have no idea what is the neighbor carbons.
Yeah.
So go for proton first.
Okay.
Alah, Dr. Tri ni saja nak tanya ni.
No, I don't understand about the NMR because
I
my
see.
research is inorganic compound.
I see. Okay, but I have experience lah evaluating master's thesis that doing the inorganic research. So since it has an organic ligand, so it still can run for NMR. And furthermore, we also has another nuclei for NMR like phosphorus. So if the compound contain phosphorus, we will go for 31 phosphorus nuclear NMR. Thank you.
very much. Pak Bambang, do you want to add the answer?
It's complete because the domain of Dr. Nurul. Oh, ya, Dr. Nurul, bagus sekali. That's good.
Okay, so for the next question for Pak Bambang, from Bu Yayu, very interesting for kinetic determination. How did Prof. Bambang determine the kinetic order of the reaction mechanism you presented?
Yeah. Bu Yayu,
I think the 3 slides, I guess, yeah, Pak Bambang, because it is in a French language, so I don't understand.
yeah. There's a slide only shown that my research is to analysis the kinetica of demethylation of ammonium salt. Yeah, we have 3 types of the reaction, and the first is anion can be used as a nucleophile auto demethylation. So if you have ammonium salt, anion can attack the methyl ammonium to produce dimethylamine. Ya, nah, itu saja Bu. I think berikutnya adalah ya selanjutnya saya hanya memberikan suatu ilustrasi bahwasanya NMR can be used as a quantitative
For kinetic.
for okay. Yeah.
So meaning that you didn't how to select and determine this is the first order reaction or second order reaction and so on.
Yeah. Yes.
So you didn't determine it.
Ya, saya mempelajari, I study, this is equilibrium. If I panaskan,
Yeah.
methyl ammonium can produce amine But at the same time, amine can react the alkyl halide to produce the ammonium salt. Oke, Bu Yayu.
Ya.
Konsentrasi saya yang tadi itu pada di situ. Itu hanya
Oke.
sekelumit. Hanya
Iya. Oke,
ya.
oke. Jadi
Ini
tidak
tiga
sampai menentukan orde 1, orde 2 gitu ya, Pak, berarti.
ini bisa, tapi tidak
Tidak.
tidak
Oke.
tidak.
Okay, maybe you can continue your data to determine the first order or second order, and then you can publish, Pak Bambang. So make how to select mengolah data lagi. Okay,
Okay.
thank you, Prof Bambang.
Thank you very much. You're welcome.
Thank you, Prof. Bambang. Is there any question for the participant? Maybe you can raise your hand. So I
Dr.
can.
Tree.
Yes.
From me, not question, but I just to add. Okay.
Okay, Pak Parsauran.
Okay.
You are more handsome than
Okay.
Bambang.
Yeah, more handsome. Yeah. Okay. Another insight of the using of the 13 carbon NMR, we can learn about the mobility of the molecule, but not by chemical shift, but what we call the time relaxation.
Yeah.
I have done this in my PhD program. I learned about the mobility of the molecule, how the mobility affect by the interaction with another molecule. This is another using of the carbon-13 NMR. Okay, thank you. Yes.
Thank you, Pak
Insight
Parsauran.
Yayuk Astuti. Okay,
Yeah. Thank you for the information. Is there anything else?
Dr. Tree, allow me to ask two questions to Prof Bambang.
Okay, come.
Prof,
Yeah.
actually, about the progress of demethylation reaction, right? Why actually you need to do that proton quantitative analysis? If you ask me, I will go for the LC analysis. During the reaction, I will just go for the LC and see either that starting material already fully consumed or not, and see either our targeted product is already formed or not. Are you doing that quantitative analysis due to the characteristic of that ammonium salt that is not being observed in TLC plate?
Iya. Ya. Begini, saya pakai bahasa Indonesia, tolong nanti translate ya.
Can.
Okay.
Also I can understand.
Okay. Your question maybe can explanation. Kemarin saya ngajar di Malaysia dan ada satu pertanyaan dari PhD program di sana. Ya. Yeah. The similar with your question. Ya.
Bukan saya ya?
No. The student PhD. Ya. Pak Bambang, saya sudah melakukan reaksi, ya. Tetapi saya tidak mengerti apakah ini sudah kok selalu gagal reaksi saya. Tidak seperti apa yang saya inginkan produknya. Ya. Kemudian saya tanyakan, reaksi kamu apa? What is your reaction? Oke. Sudah saya panaskan. Ini saya kondisinya udah ganti. Terus kemudian saya langsung isolate dan tidak mendapatkan produk sama sekali. Ya. Yang saya ingin tekankan di sana adalah yang pertama kali Anda harus lakukan sebelum isolasi, harus ditentukan dulu kuantitatifnya, apakah reaksi sudah berlangsung atau belum. That is true. Dan identifikasi di situ, apakah berapa persen rendemen dari produknya. Oke, rendemennya. Barangkali di situ ada 3 produk, ya, produk yang kita inginkan ternyata di situ adalah minor. Oke. Saya kira XPLC is oke, ya. Tetapi saya menggunakan NMR ini karena saya bisa mengikuti tanpa adanya tambahan eksternal standar. Standar yang kita butuhkan itu tidak perlu. Oke. Satu contoh aja, berapa persen produk saya, hasil saya ini, saya bisa monitor setiap waktu. Saya ambil, kemudian saya analisis NMR-nya, apakah produknya sudah berjalan 25%, apakah 50%, ataukah 70%, ataukah sudah kuantitatif 100%. Ya, itu bisa kita ikuti melalui dengan NMR. That is true. XPLC can be used untuk analisis persen transformation seperti itu. Oke, Dr. Syafiqah. Tapi
Okay.
saya langsung pakai. Ini NMR saya itu sampai 100 lebih saya. Jadi dalam disertasi saya menggunakan NMR itu mungkin lebih dari 100 ya untuk NMR.
Are you actually investigating the optimal reaction time for that reaction?
Salah satunya ya. Ya.
Oh,
Itu
okay.
yang ditanyakan oleh Bu Yayu tadi ya. Di Bu Yayu ada suatu equilibrium, ada suatu keseimbangan reaksi di situ, dan saya menentukan bagaimana mekanismenya, kapan terjadi demetilasi, kapan terjadi metilasi ya. Jadi arahnya bolak-balik. Itu salah satu contoh. Ya, itu hanya sedikit S3 saya, itu hanya 1/10-nya. Yang
Prof,
90%
Prof, actually the question that made earlier is not HPLC but TLC, thin layer chromatography.
okay. Yeah.
So okay, I got the point. Now I understand why we need this quantitative analysis. The second question, the image in your final slide is your sons or your students?
Ya, maco ya. Saya sendiri dan
Son-in-law candidate.
Your research team.
Ya, my research
I
teams.
see. Okay.
Itulah keakraban. Kalau kita
I see.
masalah beragam itu adalah kolega saya.
Alright. Okay. Thank you.
Without his wife.
Dr. Mini.
Okay, thank you. Due to the time is up, I think Bu Yayu, is it enough?
Yes, enough. Dr. Tri, I want to call Dr. Tan. Dr. Tan is here. Hello, Dr. Tan.
Yes, Dr. Yayu.
Dr. Tan, because this is the last for our joint webinar, maybe you can give like a closing remark for this joint webinar. Yeah, Putri, maybe we can give
Yes.
Dr. Tan maybe a minute or 2 minutes. Okay, thanks.
Okay, thank you, Dr. Yayu, and also thank you, Dr. Tri, for moderating this session. So I don't have much to say, but I am really how to say indebted to Dr. Yayu for your hard work and your efforts to organize this international joint webinar between USM and also Undip. So in fact, we planned, I think, not long ago, just about 2 months ago, and we successfully organized this with the help, of our faculty members, with my also section members as well. So I believe that after the visit, the officer visit from by you and also the Prof. Adi, we have many plans for 2025. So I believe that today not only the last activities between Undip and also USM. We will look forward for more activities, more collaborations between Undip and USM in 2025. So with that, thank you.
You are much welcome. Okay, Bu Yayu, is it enough?
Okay, enough, Dr. Tri.
Okay, yeah. At the end of this webinar, I would like to say thank you to Dr. Nurul Syafiqah Rezali and Professor Dr. Bambang Cahyono, also to Bu Yayu and the committee, and to all the participants. See you on the next webinar. Have a great day. Have a great weekend. Bye.